This demonstration is how to conduct a chi-square for goodness of fit. And please note that the chapter that covers chi-square goodness of fit also covers a chi-square for independence, but we're not going to cover that. If we had more time, we may, but we just don't. So we're going to stick with the chi-square for goodness of fit. And for this example, we are going to use a variable called year. And the year is kind of like the year you are in school. And what that means is that you are either an upperclassman or an underclassman. So let's look at the variable called year. And it's the year in school. And 1 is underclassman and 2 is upperclassman. It's measured at the nominal level of measurement, which is one of the requirements for a chi-square for goodness of fit. You have to have a variable at the nominal level. What we are aiming to do is to determine if there is a significant difference in the observed proportions and the expected proportions of a particular variable. For example, let's say that we have year in school as upperclassmen and underclassmen, and if we randomly sampled a bunch of people, we would expect half of them to be upperclassmen, half to be underclassmen, and that is the assumption that we're going to use for this particular test to determine if there is an equal proportion of upperclassmen and underclassmen. And if you're kind of thinking about that, you should be thinking that 50% will be underclassmen, 50% will be upperclassmen, and that's what we expect. We're going to determine if our sample is significantly different than what we expect. In order to do this, we go to Analyze, Non-Parametric Tests, Legacy Dialogues, chi-square. For a test variable, we need to find our year variable and load it into our test variable list. Let's look at some options. Are there any options that we're interested in? My dialog boxes keep popping up off screen. We can do descriptives. It won't be incredibly helpful because it's a nominal variable, so the measures of central tendency aren't going to work except for maybe the mode, but that's about it. Click Continue. Now, our expected ranges, we're going to get that from the data. That's okay, we leave it there. Our expected values are what we need to be concerned about. And we're going to expect all categories to be equal. There are 2 categories of year, upperclassmen and underclassmen. We're going to tell SPSS to assume that there are even amounts in each group if the null hypothesis is true. So if the null hypothesis is that the observed and expected frequencies are the same, then it's going to think that the observed frequencies should be 50-50. Which is what we would expect if there were no difference. So we're going to leave that alone and click OK. Our output has 20 people in it. There are 20 people in our sample for the variable year in school. The mean year in school is 1.25. That's a very meaningless statistic because you can't say that the average year in school is 1.25. Yes, you could say, well, that's somewhere between, maybe a freshman and a sophomore. It's during your freshman year. Yeah, but that's not a very meaningful thing. Standard deviation is meaningful. The min-max isn't meaningful either. So really, our descriptive statistics don't give us a whole lot of information except for n. N is interesting. Now, the frequencies for our chi-square test are that we had 15 underclassmen and 5 upperclassmen. We told SPSS to assume that there would be equal amounts in each group. So SPSS expected 10 people to be underclassmen and 10 people to be upperclassmen. The residual is the difference between the expected and the observed. So expected minus observed, observed minus expected is 5. For upperclassmen, 5 minus 10 is -5. And if you remember the formula for chi-square, it's the sum of the observed frequencies minus the expected frequencies squared divided by the expected frequencies. All of that information is here. You just have to do a little bit of math and you have your answer. But our chi-square statistic is calculated for us. The chi-square value is 5.000. It has a note A that says that 0 cells have expected frequencies less than 5, meaning that all of our expected frequencies are greater than 5. One of the assumptions of a chi-square test is that you have more than 5 in each expected group, and we do, and that's okay. So the chi-square, which is the sum of the observed minus expected frequencies squared divided by the expected frequencies, is 5.0. We have 1 degree of freedom because it's the number of groups minus 1. our asymptotic significance, which is what we use for our significance, and when you see the graph that tells you what the chi-square looks like, you'll understand why it's asymptotic. Well, if you have an understanding of asymptotes. It's okay if you don't. Our significance is 0.025, meaning that the significance of our chi-square value is less than 0.05, so that means we have a significant difference between our expected and observed frequencies. As a matter of fact, we have many more underclassmen and many fewer upperclassmen than what we would expect. When we only have two groups, this proportion is going to change the same. So if we have 16 underclassmen, that will mean that we have 4 upperclassmen, and that changes at the same rate. So you have the same amount of people. Obviously, you have to distribute the observed numbers among two groups. They're going to change fluidly. But in this example, we have 5 upperclassmen, 15 underclassmen. That's a significant difference between what we'd expect. I look forward to seeing what you can do with this, and make sure that you adhere to the guides, the templates, and the results sections guide that I gave you. I look forward to seeing what you can do.